Hello, everyone. Welcome back to my channel. Today, I will be talking about a NeurIPS 2022 paper about explainable AI. So the title of the paper is "What You See is What You Classify: Black Box Attributions." So this is actually a feature attribution methodology paper, which means that given a black box classifier, you want to assign each input feature an importance score so that you know which features are more important than others. Okay. Before diving into the paper, let's look at an interesting thing in this NeurIPS 2022. So in their open review website, if you actually search the keyword explain, it will give you a bunch of papers related to explainable AI. And we can find out that a lot of the papers are actually about explaining reinforcement learning. I guess there are two aspects of reasons behind this. So first of all, in recent years, there are fewer methodologies that are model agnostic, which can apply to different learning paradigms, different models, etc. Because this explainable AI field is pretty much saturated. So people start to looking at, for example, explaining other paradigms such as reinforcement learning or explaining a specific neural network structure, such as graph neural networks. Okay. Another important aspect is that people start to put a lot of attention to the safety and reliability of reinforcement learning, because if we want to deploy reinforcement learning in large scale, then we must ensure that we understand how it really works. Okay. Okay, so let's go back to this paper. So first of all, let's look at a little bit about the abstract. So they mentioned that an important step towards explaining deep image classifiers lies in the identification of image regions that contribute to individual class scores in the model's output. So basically, this is what feature attribution methods are doing, what input regions are important, what input regions are less important. Okay. And then they start motivating their work. Most existing approaches find such attributions either using activations and gradients or by repeatedly perturbing the input. So obviously, there is a very famous class of works that uses input gradients to actually do this feature attribution thing. And another class, for example, represented by line, the sample points around the data point in question, so they can, for example, simulate the decision boundary around the data point being explained. Okay. And then they start talking about their work. We instead address this challenge by training a second deep network, the explainer, to predict attributions for a pre-trained black box classifier, the explainable. Sorry, I'm really bad at pronouncing this word, so forgive me if I gave a wrong pronunciation, but let me just call it explainable. Okay, so the network being explained is going to be freezed in their work, and then they use a separate deep network to do the explanations specifically. Okay. Okay, so they also have some statements about their experimental results, but I have some opinions on this, but let's talk about this later on, okay? Their main methodology is outlined here, or the main structure. As previously mentioned, there is an explainer that is purely responsible for generating explanations. So for each specific input image, for example, something like this here, it goes into the explainer, and then for each specific output class, there is an associated explanation mask generated. So the mask is specifically a binary mask composing of 0 and 1s, okay? So in this scenario, there are two label classes, class 0 and class 2. It is actually greater than 1 because I guess that the authors are assuming a multi-label classification scenario. So what the authors do is that they combine the masks with respect to the label classes through a pixel-wise max operation. So basically take a union of all the relevant regions for the prediction, combine them together, and for all the non-label classes, they do the same thing and then also get the combined mask. In addition to this, they also generate an inverted mask. So basically, they invert the 0 and 1s in the original combined mask. As a next step, they combined the mask as well as the inverted mask with the original image using point-wise multiplication operation to get the masked version of the input image. They then feed the masked version of the input image into the frozen explainable, okay, and then get the according logits. So that's the basic structure of their their paper. So first of all, they have an explainer which is responsible for generating binary masks. They combine the binary masks of the label classes together and combine the binary masks of the non-label classes together. And then they generated inverted masks. And as a final step, they generate the masked versions of the input image based on the binary masks, and then feed those masked versions of the input images into the pre-trained classifier and get the according logits. A very interesting part of their paper is actually the loss formulation. So as can be seen, there are 4 components in their loss formulation. So the classification loss, the negative entropy loss, the smoothness loss, as well as the area loss. So the first 2 are kind of related. Remember that they feed the masked versions of the image into the frozen explainable and get the according logits. This idea is actually a little bit similar to a paper that we did last year. But what they do here is actually to use we also utilized masked versions of the image, but we utilize the masked versions of the image based on explanations to train a good representer through contrastive learning. And they use the masked version of the image to actually train a separate explainer that is used to explain a pre-trained image classifier. So it's actually quite different. So the classification loss is actually responsible for encouraging the masked version of the of the image that contains the important regions or the relevant parts of the image to have as much discriminative information as possible, because they want a very good cross entropy loss. Okay. Another part is that they want the irrelevant part of the image to contain as little discriminative information as possible. They do this through a negative entropy loss. They encourage the outcome to be as uniform as possible, which means that the model is uncertain in terms of the prediction based purely on the irrelevant part of the input image. A third loss component is actually the area loss, which basically they regularize the size of the important region of the image within a certain scope or a certain range. They do this through imposing a minimum threshold and a maximum threshold. So the area cannot be under the area, the size of the important region cannot be under the minimum threshold or exceed the maximum threshold. Otherwise, it will be penalized through this loss term here. I'm not going to go through the detailed mathematics here, but you can see that they played some mathematical tricks here to actually realize this functionality. One last thing is actually the smoothness loss. So the core idea here from my analysis, they try to ensure that the explanations or the important parts are actually connected with each other. They want to avoid the case that the important regions or the explanations are all over the place. Here is one piece, here is another piece, and they're distributed randomly. They try to avoid this, and they try to make sure that it's centrally connected. So they do this through the total variation loss. What they do is that they encourage the nearby pixels to have similar values. For anyone who is interested, we did a work last year that utilizes masked images based on explanations from existing explainers to jointly improve contrastive representations as well as explanations. So if anyone is interested, I will put that link below this video, okay? And that takes us to the experimental part of this work. And I do want to say something about this part. So if you actually look at this paper, what they do is basically mainly segmentation, semantic segmentation tasks. So first of all, they do a visual comparison between their methodology and other explanation methodology, for example, the GradCam as well as RISE, etc., etc. And these examples may be cherry picking, but it actually shows something. Their object capturing capability is actually very strong, and this actually shows that they could be a very strong semantic segmentation model. Okay. And 4.2, they talk about class-specific masking. And the 4.3 talks about segmentation accuracy. So their evaluation metrics they use actually mainly depend on a given semantic segmentation ground truth. Okay. However, should that be sufficient to show that their explanations are good? I don't really think this is the case, because segmentation, the good performance of segmentation actually means that you can recognize the object in the image very well, but the object part of the image is not necessarily actually the most discriminative information in your classification tasks or other kinds of tasks. It looks wild to human beings, but it doesn't mean is that it is actually the important region in the machine decision-making process. Okay. So actually, if you look at the review comments from the reviewers of this paper, so the EC will also support incorporating a user study, since the final goal of these attributions is to provide visual explanations for human users. They mentioned that their empirical work is actually not very sufficient, and they suggest user study. But I don't think user study itself is actually sufficient, because if you look at some recent works that defines explanation faithfulness, so faithfulness is actually the quality of the explanation. Okay, if an explanation is faithful, which means that the explanation itself is very good. So it's faithful towards the model predictions, which means that it explains the model predictions very well. Okay. So here in this paper, this is a very well-known NLP paper in natural language understanding domain. Okay, towards faithfully interpretable NLP systems. They specifically mentioned that faithfulness evaluation should not involve human judgment on the quality of interpretation. Okay. Again, the explanations may look good to human beings, but that doesn't mean that the explanation is faithful towards model predictions, because if human beings are already knowing what models are thinking about, then why do we need explanations at all, right? And that is basically the main point of this argument here. So in my master's graduation thesis, which is already published, titled Explanation-Driven Frameworks for Data Augmentation and Supervised Contrastive Learning in Image Classification, we provided a short summary on explanation faithfulness. Okay, here, specifically, we mentioned a paper called Eraser. So here, this paper, Eraser, a benchmark to evaluate rationalized NLP models that give a specific rigorous mathematical definition on how explanation faithfulness should be defined. Okay, so simply speaking, there should be a causal relationship between the perturbations, input perturbations based on the explanations, and the output confidence scores changes. Okay. But in this paper, I don't actually see, according to my observation up to now, I don't see any causal relationship evaluation in their empirical part. So for anyone who is interested in reading our summary about explanation evaluation, I will provide a link to my master's graduation thesis to this video. Okay, so thanks very much for watching today's video. That's it for today. Thanks very much for supporting, and I look forward to seeing you in the next videos.